Okay. Welcome everyone to our weekly Astro Seminar. This week at a special time, special day, because on Thursday we have Hanukkah, and Shahar Hadar here is actually here to talk about light from black holes, which is very fitting for this festive occasion. Shahar did his studies from undergrad to PhD at the Hebrew University, and then went on to a tour of postdocs at Cambridge, at the Max Planck Institute, and now at the physics department in Harvard. So, Shahar, please tell us about photon rings and light from black holes.
Okay, thanks very much. Thanks for the opportunity to speak here. So I'm going to tell you about photon ring autocorrelations. And this is related to the first image of the black hole that we witnessed last year. A great achievement, in my opinion. But of course, there's still a lot more to do. This is only the first image. In particular, it would be great to get better resolution. Even though already getting this kind of resolution of horizon scales is really a big achievement. But it's interesting to think, what could we achieve? What could we see if we had better resolution? And also kind of to try and think, what kind of ways can we see these features with? So a black hole has a lot of interesting structure, which currently is not resolved in the image. But it's interesting to think.
Okay, can I ask quickly? I mean, can we get a better image? So the telescope they use has a baseline of the entire Earth, basically.
Right. So yeah, in principle we can, but we would need to. Basically, there are two ways in which to do it. One is to achieve a larger baseline by sending a mission to space, and the other is by increasing the frequency. But that's currently a problem because of absorption in the atmosphere to go to higher frequencies. But in principle, we could. And this is actually part of what I'm going to tell you about today, our proposal to actually send a mission to space and to achieve a longer baseline. But afterwards, I'll tell you about the autocorrelations in which you really don't need a larger baseline, and you can still infer things about the fine structure of black holes, but it's not. But that's not talking about the image. It's talking about other observables. So, but yeah, definitely I'll get to that. This is the goal of what I'm kind of trying to say. How can you achieve better? How can you achieve more information on the black hole? So this is, of course, that was the picture of the black hole in M87, and this is just a simulated image that was made by the Event Horizon Telescope collaboration. So what does a black hole look like? In principle, this is a question which is affected by two main things. One is the complicated astrophysical phenomena, which happens in the vicinity of the black hole, accretion dynamics specifically, which generates the lighting for the black hole. And the other is general relativity, which in a very unique way determines the geometry around the black hole, and in particular acts as a lens for this light, which is generated by the accretion flow. So these are kind of the two. One is the light generator and one is the lens. And this question has been studied since the 70s. It was pioneered by Bardeen, Luminet, and others. And the point is that since it depends on these two pillars, there are some features of the image which depends on the astrophysical parameters, such as the configuration of magnetic fields and the temperature of the plasma, of the accretion flow plasma, and others which depend only on the mass and spin of the black holes. So they're very universal. So you can see here 4 different images generated by the EHT collaboration, and you can see that some features are more universal than others. In particular, one universal feature that appears is the so-called photon ring, a bright brightness enhancement of a circle-like shape. It always appears in the same place in the image, but other features such as the brightness of the rest of the direct image, so-called the part which is not the photon ring, that's that differs in different images. So how do we calculate what is the image of a black hole? Say we knew what the accretion flow is. How do we calculate what the image is? So this is done by ray tracing or by radiative transfer. How is this done? We think about an observer very far away from the black hole. This is the screen of the observer. And we shoot back null geodesics from different points on the screen into the bulk. And we kind of collect all the photons that board this geodesic as this geodesic intersected emitting matter. So this will tell us how bright this point will appear on the screen. And you can think of different points on the screen of the observer as parameterizing the different conserved quantities of this null geodesic, the angular momenta specifically, or impact parameters more precisely. So different points here define different impact parameters, and then we shoot back the geodesic and just we follow it into the bulk and see how much emission it collected as it intersected the emitting matter. That's how it's calculated in practice. And this is the equation. It's called the radiative transfer equation. Curly I is the specific intensity at the point on the screen. Sigma is an affine parameter along the geodesic. Curly J is the emissivity at a point in the source. This tells us how much emission there is at some bulk point. And there's also an absorption term, which we will neglect today, saying that this emission is optically thin. Okay, but in principle, we could have also had an absorption term. Okay, so to understand how an image of a black hole looks like, we need to understand light propagation in black hole geometries. And we can start from Schwarzschild, which is the simplest case. So in Schwarzschild, we have the energy and angular momentum are conserved. And if we use that in the geodesic equation, then we reduce the problem to a one-dimensional effective problem of motion in some effective potential. So this is kind of how this motion looks like. And then you can think of this one term as an effective energy, and this V is an effective potential, and this is an effective... Sorry? Was there a question or, okay.
Just noise,
Yeah, feel free to stop me, of course. So we can think about this problem as follows. We send in a particle from infinity with energy 1, and then depending on this coefficient of the effective potential, which is rho, the impact parameter, L over E, we have two different behaviors. If this rho is large enough, so the impact parameter is large, I'm shooting the photon not so close to the center of the black hole, it will just bounce off the potential and go back to infinity. But if the potential is now, the maximum of the potential is below 1, this photon will fall into the black hole. And there's the marginal case in which the potential exactly reaches 1 at its maximum. And then we have a critical orbit. We have a photon coming in from infinity and spending arbitrarily long time near the peak of the potential. In particular, we have also a unstable spherical or unstable critical orbit in which the photon sits exactly at the top of the potential indefinitely. But this is, of course, an unstable orbit. So the criterions are that this potential and its first derivative vanish. So it's a double root of this potential. And it's always unstable. So the second derivative is positive. And for Schwarzschild, this happens at a very specific radius, r equals 3m, which is the photon sphere. And for a very specific impact parameter, rho tilde, which is 3 square root of 3 times m in relativistic units. So, okay, these are very special orbits, very fine-tuned orbits, but we can also ask what happens near these critical orbits. So we can expand near criticality as such, and plugging this into the effective potential, we get a very simple expression for it, depending on the deviation from the radius and the deviation from the critical impact parameter. And using that, we can show that the total, for example, the total azimuthal angle, which is traversed by a near critical photon, diverges logarithmically with how close we are to the impact parameter. So this is just saying what I said in words before, that as I tune the photon to be very close to critical, it can spend an arbitrary long time and keep orbiting the black hole. And this is, and exactly the total angle that it, azimuthal angle that it traverses, is logarithmically divergent in the distance from the critical impact parameter. Okay, and we can also invert that relation and say that if we want to shoot a photon so it undergoes, say, n half orbits around the black hole, n will parameterize here the half orbits, just for my convenience. So we need to shoot the photon exponentially close to this, to a certain curve on the screen, which in Schwarzschild is defined by this critical value 3 square root of 3 times m. And in general, it's called the critical curve or the edge of the shadow of the black hole, which is the critical surface delineating the photons that, separating the photons that if I shoot them towards the black hole, they fly off eventually to infinity. And those that if I shoot into the critical curve, they fall into the black hole eventually. And the critical photons are those that if I shoot exactly on the critical curve, then they will end up orbiting the black hole an infinite number of times. That's also true in Kerr, but in Kerr, this curve will not be just a circle, it will be more interesting. And we'll get to that. Okay, and this logarithmic divergence in the total accumulated angle is the reason for the photon ring, is the reason for the brightness enhancement, at least for optically thin emission, because if I have a light ray that undergoes many orbits around the black hole, as it undergoes many orbits, it picks up more and more and more photons. So it turns out that these near critical orbits, the way they appear on the screen is with an enhanced brightness. Okay, and we can, just to get more intuition into the Schwarzschild case, we can look at a situation in which we have this black hole here behind this shadow, and we have the edge of the shadow, a Schwarzschild black hole, and then we have some light source here, which I just depicted as another black hole. We can think of this situation, and then we have one image coming from a light ray which travels directly from the source to me. This is what I, oops. This is what I would call, oops, sorry. This is what I would call, I don't know what's happening here. This is what I would call the n equals 0 image. But then there's another image coming from a light ray that went behind the black hole and came to my eyes from the other side. This would be the n equals 1. And then I have an n equals 2, n equals 3, etc., which come from light rays that underwent a certain number of half orbits around the black hole, and they all asymptote to this critical curve. But also these images get exponentially demagnified or squished to this critical curve. So they become kind of smaller and smaller, sharper and sharper if I had infinite resolution. If I have finite resolution, they do get smeared. I mean, eventually the flux in these images is small. But we will discuss all these points. And also we have this other family of images inside the critical curve. So imagine that we have some star in between me and the black hole. So I see one image of that. Oops. Okay, I see one image of that. The n equals 0. Then I will see an n equals 1, an n equals 2, etc. So there's also, they also asymptote from the inside of the critical curve. All the images, and I can divide the sky into subrings in which I get photons that underwent a certain number of half orbits. So in this region, for example, I only get photons that are direct. In this region, I get photons, I get both direct and ones that underwent 1/2 orbit, 2/2 orbits, etc., etc. So these subrings asymptote to the critical curve from both sides. And if you want to be very prosaic, you can say that there's an infinite number of images of the whole universe near this critical curve, because at least mathematically, ideally, every source can be connected to every observer through an infinite number of geodesics. Yeah.
So these, just to make sure, so these two sources are at the same plane. So they're not in front of the black hole or not behind the black hole. They're in the same plane of the black hole.
Wait, this source and this source?
Yeah, I mean the ones that, yeah, this one and the one in the inner region.
They don't have to be in the same. Here I drew it as if there's not. They don't have to be in the same. Like I'm thinking about the plane defined kind of by the observer, the black hole, and the source. So
Yeah, I
this
mean, are the observer and the black, not the observer, are the black hole and the source, are they have the same distance? Or because if the source would be, let's say, in front of the black hole, right, you'd have some image that goes around the black hole, but it would be very, very dim.
I don't think it has to be very dim. I mean, there is this effect of demagnification, so there will always be some exponential suppression of the flux because the image is much fainter. But in principle, you know, this kind of image and this kind of image and this kind of image, if the emission is optically thin and neglecting redshift effects, I would say they can have this like same order of magnitude of specific intensity.
Well, I'm just asking, where are you locating the source?
I'm locating the source between the observer and the black hole. Somewhere kind of, it can be, if it would be exactly on the axis between me and the black hole, it would be here, but then it would be kind of a singular case, I guess.
I understand, but you know, if this is the black hole, you know, I'm the observer, right? That's it, and this is the black hole plane, right?
Mm-hmm.
So you're putting the source on the same plane, or are you putting it, you know, in front, you know, in between me and the black hole, or behind the black hole? It was ever made on what you're saying.
I was thinking about the situation in which this is the black hole, I'm the observer, and it's in between.
Then the image that goes, what you call N1 here, would be very,
Right.
very dim, right? It would be much dimmer because the light rays has to go the other direction and cross the black hole.
That's true, but there's no, I mean, except for the demagnification issue, I don't think it has a reason to be dim. Why would it be dim?
Because of the demagnification.
Right. So that is true, but that is true in the same case for these guys too.
Yeah, that's true. That's why I asked if you put all of them in the same plane.
Right. Right. Like
So-
the brightness would be the same, similar at least, up to redshift. There are redshift issues. So there are issues like, for example, if this is the black hole and I'm the observer and this is the source. I mean, it could be also the case that the source is falling into the black hole. So the first image would be actually redshifted, but then the second image that goes around and comes back to me would be actually blue shifted. So there is also situations like that in which, I mean, this depends really, it's a Doppler thing. It depends on the motion of the source.
Yeah, but since you're talking about 3RG, if you got into if the source is so close to the black hole, right, 3RG, then yes, it's a very transient source. It's not going to last very long. When you're showing
Right.
like a kind of a static image.
Right. Yeah, I agree.
Well, you could have the edge of an accretion disk would be there for a long time, the inner edge.
Yeah, but it won't be a single point like source as is plotted here.
Right. It will be like rapidly varying. That I totally agree. I mean, yeah. Okay, great. So that's the story of the subrings. And now we can discuss Kerr. So in Kerr, the situation is a bit more complicated, but also a bit much actually more interesting. So in Kerr, it turns out that in a non-trivial way, we have enough conserved quantities to also solve analytically for these geodesics in a more non-trivial way than Schwarzschild, because so in Kerr we have axis symmetry and we have time translation symmetry, and we have this mass which is always conserved, the mass of the particle, which in our case is a photon, so it's 0. But the fourth conserved quantity that allows us to solve these equations is the so-called Carter constant, which is due to not to a killing vector field, but to a killing tensor field. Okay, but and yeah, in the end of the story, we have these 4 conserved quantities, and since we're dealing with photons which have 0 mass, we actually have only 2 meaningful conserved quantities since the energy factors out of these angular momenta. And the only important conserved quantities or impact parameters are these lambda and eta that I define here. It's the rescaled azimuthal angular momentum and rescaled Carter constant. This Carter constant is related to the motion outside of the plane, outside of the equatorial plane, or to the polar motion. So it's 0 for geodesics that are that reside in the equatorial plane, and it's larger for geodesics that actually oscillate around the equatorial plane, for example, or have some polar motion. And it's given by this expression. Sorry, I forgot to show. It's given by this expression. So P theta is the angular momentum in the polar direction, and theta is the polar angle. So it's some combination of angular momentum and angle that is conserved. The radial equation of motion in the Kerr case will be something, again, slightly more complicated than in Schwarzschild, but also defined by some effective potential, which depends only on the radius and these two impact parameters, lambda and eta. And the critical photon orbits will be still defined by the same condition that this potential and its first derivative are 0. But in the Kerr case, the situation is more interesting since we don't have only one photon sphere, we have the so-called photon shell, which is a region of space-time in which you get these critical photon orbits, and they're parameterized by a parameter, this r tilde, which is what the radius of these photon shell orbits is. So you see that this r tilde varies between some minimal and maximal value. For Schwarzschild, they coincide, and it's just 3m. For maximal spinning Kerr, they can range between m and 4m. So there's kind of this photon sphere gets puffed up to a region of space-time, and you get a family, a one-parameter family of spherical photon orbits. Now, similarly to the Schwarzschild case, you also get on the screen of the faraway observer a critical curve, which defines the directions in which if you shoot the photon, it will orbit the black hole an infinite number of times. But if you shoot the photon to different directions on this critical curve, so with different impact parameters, you get a photon orbiting at a certain radii, at a certain radius for an infinite time. So again, as I said in the beginning, you can think of this screen of the observer as parameterizing the different impact parameters. And each point here defines a geodesic. But now you can think about also this r tilde, the radius of the photon shell orbit, as parameterizing the critical curve. So different points on this curve actually corresponds to different radii in the geometry. It's very counterintuitive because you were used to looking, for example, at an object in the sky, and different angles on this object define different angles on the object really in the bulk. But here, you're looking at different angles of the screen, and it's defining you different radii in the bulk. And there's a similar story like in Schwarzschild. There's a brightness enhancement near this critical curve arising from geodesics that went around the black hole a large number of times. And this will generate a divergence on a brightness enhancement, which is also a logarithmic divergence in the distance from the critical curve. But now this divergence will have some coefficient, which is non-trivial and depends on this r tilde. So at different points on the curve, we have a logarithmic divergence with a different coefficient. So it's kind of a different magnitude. And this magnitude is determined by this so-called Lyapunov exponent of the orbit of that r tilde. This Lyapunov exponent is roughly the second derivative of this radial potential. So it tells us something about how unstable this photon orbit is. For example, if this photon orbit is unstable, but only a little unstable, so the potential is kind of almost flat there, the photon can still undergo many orbits before it flies off either to infinity or into the horizon. And then it can get more significantly enhanced because this enhancement goes like 1/gamma. So for small gamma, it will be a large enhancement. But, and of course, the inverse is also true. If the orbit is very unstable, it can't spend a lot of time in the photon shell, and then it will not get significantly enhanced. So that's the origin of this gamma appearing here. Good. And this is also telling us, this equation is also telling us that as in Schwarzschild, in order order for the photon to undergo n-half orbits around the black hole, we need to shoot it exponentially close to the critical curve. It's exponentially, but now with this factor of gamma in the exponent.
I have a question.
Yeah.
Wouldn't the photon simply move if it's it's metastable, let's say, right? So it will just move along this curve, but when it reaches regions in the curve which are less stable, right, it will just diverge from the curve there more likely than in other places.
Sorry, it will diverge from the core.
Right. I mean, the photon. You say that the photon will stay along the curve, right? There is some it's unstable, really. It's metastable.
Right.
If it's very close to the curve, right, it will still stay along the curve. It will just follow the red curve, right? If for this value of the spin, right? But when it reaches a region along that curve in which the exponent is larger, it will just diverge the curve there.
Sorry, I wasn't saying this clearly enough. This diagram is the screen of the observer. So I'm thinking of every point here as defining a certain lambda and eta. And then, this point here does not change. It's one, once I pick lambda and eta, that defines my null geodesic. And then I follow it into the bulk. So it does remain with the same lambda and eta at all times.
Oh, I see, I understand that. But then consider a photon now. Right now, a photon goes along, this photon curve, right? The equivalent of the 3RG for
the photon shell, what they call the photon.
The photon shell, right?
Yeah.
Now it will stick along the same curve, right? But when very close to it, it's not exactly on the curve, but it diverges a little bit. But then when it reaches regions where the Lyapunov exponent is larger, it will just diverge there, or more likely to diverge there.
Well, I mean, but this Lyapunov exponent is determined once and for all by your choice of the point on the screen. So, I mean, you do follow the kind of the characteristic life of this near critical geodesic as you shoot it back towards the black hole. It does spend a lot of time near a certain radius, but it only has one photon shell radius. So it climbs up towards this radius, and then it can either go back to infinity or fall into the horizon. But its Lyapunov exponent is determined once and for all, once it's shot back from infinity.
Well, that's fine. Okay, thank you.
Okay. Okay. So just to get a little bit more intuition into this story, we can look at this cool demo made by Leo Stein, which I use a lot because it really nicely exemplifies all this one parameter family of photon shell orbits. So we can look at the case of a black hole, for example, of high spin, just to see the effect pronounced, maximally pronounced. So if we look at very large radii, the first photon shell orbit is the counter-rotating circular orbit. And then we can kind of go into lower radii. We're now running along this parameter that, as I told you, parameterizes this one parameter family of geodesic. So we have orbits that now go out of the equatorial plane. They oscillate in the polar direction. This is kind of the exactly critical orbit. So they oscillate in the polar direction, and they also keep moving in the azimuthal direction and in the time direction, of course. And but they stay at the same radius. And as I reduce this radius parameterizing them, I get also to the geodesic that actually closes to a sphere that actually manages to reach the pole. Because that's actually the geodesic that has zero azimuthal angular momentum, lambda equals 0. And as I lower the photon shell radius, I reach these geodesics that actually are co-rotating, and the end with a geodesic that is a circular co-rotating orbit. That at maximal spin, it actually reaches very, very close to the horizon. So at maximal spin, you also have a photon shell orbit, that's very, very close to the black hole horizon. And that's the family of orbits. Another interesting thing that can be looked at and will be relevant for the second part of the talk is the effect of spin. So if we look at these photon shell orbits, so this is now very low spin. You can see that the orbit undergoes with like the change in azimuthal angle with each half orbit is exactly pi. So you have the photon that emerges from here. After one half orbit, it will emerge from here. So so the change in azimuthal angle is exactly pi between these two sides. But as I crank up the spin, you see there's a frame dragging effect, which can become actually very significant, as you can see here. Okay, so you can see actually that a photon that can emerge from one side of the black hole and then can undergo one half orbit, but not come again from the other side, but from some shifted position, which depends on the spin of the black hole. And this is a frame dragging effect. This will be important for the correlations part. Okay, so I already told you guys about this paper that we had last summer, where we studied the structure of the photon shell and the photon ring. And this is a collaboration of people from the Event Horizon Telescope, led by Michael Johnson and these people. So we studied the structure of the photon shell and the photon ring, and what could be the observable signatures of this structure. So this is kind of, again, an exemplification of what I told you about. We have a one parameter family of photon shell orbits between some minimal and maximal radius. We have one special photon shell orbit which actually manages to reach the pole and close. This is the zero angular momentum guy. And this is the way in which the photon shell appears on the screen. So, sorry, the photon ring appears on the screen. So the photon ring depends not only on the mass and angular momentum, but also on the inclination angle. So if you look at the black hole exactly from the pole, like face on, we see an exactly circular critical curve, and we managed to probe only one photon shell radius. But as we increase the inclination, we have access to more photon shell radii, as demonstrated by the colors here. So we can see more photon shell radii. And also the shape of the photon ring becomes a bit more deformed. But if we want to see a very significant deformation of the photon ring, we need to go to pretty high spin and also to closer as possible to the equatorial plane. There you would see significant deformation of this shape, which depends on the spin and inclination. Okay, great. So in that paper, we showed that the photon ring is made up of near critical photons. So this is just to show how the image is built up. So we have one image, which is the direct image, the n equals 0 image, which comes from photons that don't go any extra half orbits around the black hole. But we have these n equals 1 guys that do undergo a half orbit around the black hole. And these appear exponentially closer to the critical curve. And then we have the guys that undergo 2 half orbits around the black hole, and they appear even closer to the critical curve and generate this very fine feature on the screen. And the total image is made up of the sum of all these guys. So this kind of looks pretty similar to the images that I showed you in the beginning. Now, what we studied last summer is this point that if you look at a kind of generic emission scenario, concentrated kind of at these radii close to the black hole, like this is a view from above. So there's kind of an annular region in which the emission is strong, and then in the polar direction, it's concentrated around the equatorial plane, but it doesn't have to be very thin or anything. So under these kind of mild assumptions on the accretion configuration, on the emission configuration, we showed that if we're considering the subrings, the guys that actually are generated by photons that underwent a certain number of half orbits, which is non-zero, there's a symmetry in the image. So the n+1 subring, its time averaged image, is equal to the time averaged image of the nth subring, only it's lensed or demagnified by this factor of e to the gamma. So at each point on the image, there's a demagnification factor, but it's different at different angles on the image. So, but the profile in the orthogonal direction, in the row direction, stays kind of the same profile, only it's squished by this factor of e to the gamma. So this is just to exemplify this, this point. Let's say we make a cut here through the photon ring. So we see the photon ring is composed of a sum of subring contributions. This is one subring contribution, this is the other, and this is the other, and there's an infinite number ideally. And all these contributions have exactly the same shape, only they're demagnified by a factor of e to the gamma. And this is a strong prediction of GR, because this demagnification factor is different at every angle. So if you can actually measure this say you can measure two subrings and compare their width at different angles, you have really a pretty strong test of GR here. Of course, it's hard to measure, specifically because the rings are exponentially decaying in area on the screen and therefore also in flux. The intensity is of the same order of magnitude, but the flux is suppressed. However, we argued in this paper that since VLBI, very long baseline interferometry, actually measures the Fourier transform of the image directly and not the image itself. So the way this image was generated is by VLBI. So you kind of calculate different Fourier components of the image or visibilities through 2-point correlation functions of the electric fields in two radio telescopes. You correlate these two signals from radio telescopes from every possible pair that you have, and then you generate visibilities, which are components of the 2D Fourier transform of the image. So we know that in Fourier transform, there's a property that the high K component of the Fourier transform, or high wave number, like large frequency, that's determined by the finest features in the image. So if we have a subring, even if it's not very bright, but it still has finite brightness, but it's very, very thin, that's the thing that will actually dominate the Fourier transform at very high K. So our proposal, and okay, yeah.
Are you assuming, you explicitly assume that the inner part of the disk, that is the source of the radiation, truncates at radius which is much larger than that, right? Presumably several RG. Is this a reasonable assumption?
Why do you say that I'm assuming that?
Because otherwise you got contamination from the inflow from the disk material that is already there. So I can simply ask you, what do you assume about the inner part of the disk that you plotted here? What radius are you taking?
I don't think we assume too much. I don't think we have assumed too much about that.
What would happen is that you get, if you have disk that we should have this, right? The truncates below this photon ring, right? And then you would have direct emission from the disk, so you won't have this fine structure that you're looking at.
Right. Yes, I totally agree. You'd have both direct emission and photon ring from the same region there. Right. I agree. The point.
Yeah, you didn't say that, but I assume that you explicitly assume that you have isotropic illumination from the outside, or this is not the case, or this is not needed.
I don't think it's important in our case too much, because we don't say too much what's the image of the nth ring. We just care about this relation, which is true like for n, which is non-zero. Maybe maybe for 1 it's marginal, but for n equals 2 and up, it's already pretty, it's very solid. I mean, you can see in simulations. But I agree about that. So yeah, I think this figure actually exemplifies the point that you said very well, because this n equals 0 is the direct emission. This is actually a case like you were discussing, because this n equals 0 is the direct emission. On top of that, we have n equals 1. On top of that, we have n equals 2. So they're all on top of each other. We don't really need to see them separately in the image itself, but in the Fourier transform, they get separated because some of these features are much finer than the others. So in the Fourier transform, actually the fine features go to very large K, and the less fine features go to smaller K. So they get kind of separated naturally there. And this, yeah, that's our proposal. I mean, it still needed to be elaborated afterwards on how exactly to measure it, but this was kind of the proposal. And for example, if we send the radio telescope to the moon, then we can see the n equals 2 ring, for example. And other points, we can see other rings. So that was the story from last summer. And now I can tell you a bit about the autocorrelations, which is the new work that appeared a month ago with Michael Johnson, Alex Lupsaska, and George Wong. So the question is, what next? Okay, we understood some things about the time averaged image or the 1-point function of the intensity. Now, what can we do more? So a few hints are that it's quite amazing, but the EHT takes so much data that actually the data taken at each radio telescope, which is basically this E of t, this electric field as a function of time emitted from a certain direction in the sky, just this function E of t is too much data to be sent over the internet. So it actually needs to be shipped physically, saved on a hard drive and shipped physically to a central correlator. Just because the sampling rate is insane. It's 10 to the 9 or 10 to the 10 hertz, because we're actually sampling the electric field with the phase coming from that direction. So, so that's a lot of data. And in the end, the images are only a few kilobytes. So there's a lot of data going to waste. And the natural question is, okay, can we infer some more information, extract more information from all this data? And another hint is that there is a lot of time dependence in the source. That's already pretty clear, even from the first 4 images that you can see here down here. I mean, they show already a variability of around 50%. And we know that accretion dynamics is very violent and turbulent, and we expect variability. And it would be interesting to think about higher point correlation functions. So the VLBI uses only the 2-point correlations of EI, EJ at a certain time separation. But in principle, if you have all these E's, you can play more games, you can measure more things. So what can you measure? So here we propose a new observable in this paper that is the 2-point function of intensity fluctuations on the screen. And these intensity fluctuations are defined as the intensity subtracting the time averaged intensity. So it's this 2-point function. In terms of electric fields, for example, it's more like a 4-point function, because every one of these I's is like a 2-point function of E's. So it's a little bit looks like a 4-point function of E's. But I mean, it really demands more work to do that connection completely, but we haven't done that yet. And anyway, we can just assume that we have the intensity as a function of time and position on the screen, and we're suggesting this observable, which is the 2-point correlation function of that quantity. So just to exemplify the idea, this is a simulation performed by the EHT collaboration, and we're suggesting to look, I don't know why this is causing me trouble. We're suggesting to look at the 2-point correlation function at different times and angles on the photon ring. So we're looking specifically at different angles and different times on the photon ring. And at each point, we're looking at this intensity fluctuation. And then our observable C will be this 2-point correlation function. We can see from this simulation that it actually is variable, kind of in a way that's not directly clear initially.
What is the simulation simulating? I see time running, but what does it mean?
Yeah, so it's actually it's a little bit cheating here because this is a simulation. It's a full GRMHD simulation, like they have in the EHT, but the ray tracing is actually done with so-called fast light and not with slow light. Fast light means that you're taking actually light rays that travel at infinite speed and not at the speed of light. So you're basically just freezing a snapshot and then doing the radiated transfer. And that's why actually these guys can't yet compute numerically the thing that we want to compute. Because for that, they will need to make a slow light simulation. And I mean, they can do it, it just demands a lot of work and time, but I guess they will do it at some point. Yeah.
What do we learn from that? So we're seeing this autocorrelation. What physically does it tell us? I might have missed this point.
Yeah, this is what I'm going towards. So I will tell you. I will tell you in the next few slides. Yeah. So just to exemplify the idea, these fluctuations have to be correlated because indeed, when you look at a black hole, at the vicinity of a black hole, imagine that you have some flare happening in the accretion disk or some other event, which is time dependent, at some space-time event. So that's connected via an infinite number mathematically, but it doesn't matter that it's infinite, several number of null geodesics to the screen of the observer. And basically all the light rays which are not n equals 0 appear very close to the photon ring. So every such event, these are two real plotted geodesics here and where they actually appear on the screen. And these are like n equals 2 and n equals 3. So you can see that they appear right on the photon ring at different times, at different positions. So that's why some correlation has to be there, but the question is exactly what this correlation is and what can you learn from it indeed. So mathematically, we can write down this correlation function in the following form. So this is this 3D correlation function, which depends on the times, angles, and radius on the screen of the 2 points. So this is how we define it. Intensity fluctuations at these 2 points. I call it 3D because it's time and so 1 time and 2 screen coordinates. And then since, as we said, these fluctuations always, not always, but all the ones that are not n equals 0 appear very close to the photon ring, then we can think of it just as fluctuations on a ring. And we can integrate out the direction perpendicular to this critical curve and just think about a 1 + 1 dimensional ring. So this is how we do it using these integrals. And if we want, we could also integrate out the angles and think about the source just as a point source, which is unresolved, but has some time-dependent intensity. And we could also look at correlations only of the light curve, which is a well-known thing that can be done. And that's done by integrating out the angles. So these are the quantities that I want to look at. And I'm interested specifically in the contribution of near critical orbits and near critical photons, as in the photon ring story that I told you before. So in order to do that, we will need to define, 2 additional critical exponents. We already have the Lyapunov exponent gamma, but there are 2 other guys which are important. Tau, which is the time period of the critical photon orbits, and delta, which is the azimuthal angle accumulated with each photon orbit. So what am I talking about exactly? I'm talking about these photon orbits as we saw in Leo Stein's demo. They stay at the same radius, but they also accumulate some time with each oscillation, and they accumulate some azimuthal angle with each oscillation. And the amount of time and azimuthal angle that they accumulate is this delta and this tau. Okay, so this is something that characterizes the specific critical radius, critical photon orbit that I'm talking about, and it depends on R tilde. So so you can now think about 3 quantities that are important to understand the lensing of near critical photons. And to exemplify this even more, we can draw a diagram like this. Now this is a rotating black hole, but the spin direction is turning outside of the board. Okay, so we're looking at it face on just from the polar axis. And now we imagine that we have some image here, the n equals 0 direct image. This will have another n equals 1 image, n equals 2 image, n equals 3. And as you can see, they're not now on the same line because the black hole has spin. There's this frame dragging effect that I showed you before. And now this triplet of critical exponents comes into play in the following way. So the relation between some image and the next image is very simply defined in terms of these critical exponents. The time separation between these two images is exactly tau. The azimuthal separation between these images is exactly delta. And the distance from the critical curve is the same up to a factor of e to the minus gamma. So this is how these three guys come into play. And it's the simplest case is in the polar case where we only have one basically photon shell orbit reaching the observer. In the more general case, we have many different photon shell radii, that depends on which angle are we on this critical curve. So it becomes a more complicated and rich story. But this is the simplest case, which is still non-trivial. And it's also kind of, and it's also still observationally relevant because M87, for example, we believe it's 17 degrees inclination. So it's already pretty close to polar. Okay, so that's the near critical lensing. Now I can tell you what's the model that we took for the emissivity. Of course, this is really the dumbest toy model that we could think of, but that still exemplifies the main idea, and it can still be significantly improved. So we wanted to take a toy model of an accretion disk, which is geometrically thin. So it's a delta function in the polar direction. And that has a two-point function of the emissivity fluctuation that has some decay and that is separable in t, r, and phi, and has some characteristic decay length in the t, r, and phi direction, characterized by this parameter LT, LR, and L phi. This is the correlation length in these three different directions. It also has this parameter, which is the overall constant, which tells us how strong the fluctuations are. Okay, so we're just really imagining a thin disk which is fluctuating randomly just with a two-point correlation function that looks like this. Yeah, okay. So just to check kind of, even though it's not a realistic, a totally realistic model, I mean, I do think that it exemplifies the idea pretty well and allows analytic analysis. And just to check, okay, so if we kind of compare this model to more realistic accretion as derived by GRMHD simulations, full numerical simulations, we can compare what are the correlation lengths, for example, in our model versus a real simulation, and that will be important for observability. So we checked actually what the correlation lengths are in a realistic GRMHD simulation with a certain spin and a certain magnetic field configuration. We checked what these are just by taking 2 points in the bulk of the simulation and checking the correlation function as we separate them in time, as we separate them in R, as we separate them in phi. And this is what we find. We find correlation lengths, which are given by 3m in the time direction, 4 degrees in the phi direction, and 0.4 m in the radial direction. So this will be important, actually. If these correlation lengths would be significantly larger, we would run into a problem. But the fact that they're actually smaller than the light crossing time, for example, of the black hole, that's good for us. And I will tell you why in a bit. So
isn't the light crossing time just m?
Sorry?
Isn't the light crossing time just m?
No, well, what I call the light crossing time is like the period of one of these photon shell orbit, the period that it takes one of these orbits to undergo a full orbit around the black hole. And that's like 15 or 16 m. And it doesn't depend also much on spin, actually.
again, this correlation is for what source?
So it's just our model source, which is just a toy model source you can think of, just exhibiting the property that the emission is random. It's it's just random, and the choice that we made, and it's a significant choice for simplicity of the calculations, is that it's separable, and also it decays like a Gaussian with some characteristic length in all the directions. But this could be improved for sure. I mean, this is just, we took the simplest case to start with.
So it's got some sort of a Gaussian shape.
Sorry?
It has some sort of a Gaussian shape around some time t prime, r prime, and phi prime, or rt and
Yeah, it's like, yeah, exactly. Like if I take 2 points and I check the 2-point correlation function of the emissivity delta, sorry, the emissivity delta J in these 2 points, then of course, if they're very close to each other, the correlation is perfect. But as I separate them, the correlation becomes weaker and weaker, and we just assume that it falls off like a Gaussian with some characteristic length. That's our assumption here.
Is there any real source that you had in mind?
Sorry?
Was there any real source that you had in mind when having that, or this is just for?
What we basically have in mind is a accretion disk around like a, you know, like an accretion flow around a supermassive black hole, but not more than that. I mean, this of course can differ between black holes, have different parameters. There are some that are thick, some are thin, and we really didn't want to input too many parameters.
Accretion do not have Gaussian in radius, right?
Good point. So this is actually we found this this is a way to generalize the Gaussian distribution to the circle that still is periodic in boundary conditions. So it's actually for when this L phi is small, it looks like a Gaussian. It just takes care of the boundary conditions like around the circle. It's called actually the von Mises distribution. Yeah.
Okay. Also, accretion disk would not be Gaussian in time; it would just be steady in time, roughly.
But this is the correlation of fluctuations in the disk.
Okay.
So because it's random, yeah, because it's random, you would expect that this correlation would decay if you take 2 very separated points.
Okay.
Yeah.
Thank you.
Great. So so this is the calculation that we did in the end for this polar observer. So we need to integrate the radiative transfer equation to know the brightness and the brightness fluctuations on the screen. But because we're taking an infinitely thin disk, then we basically just need to sum over all the crossings of the disk and sum the emissivity fluctuation with each such crossing. That's this equation. And then we need to throw that into our definition of the 2-point correlation function and perform these integrals and one of these sums. And in the end, we get a result which is a sum over peaks in the plane defined by big T and big phi. Remember this, here we're only considering a polar observer. So the answer depends only on the difference between angles on the ring. And it always will depend on the difference between times because we're assuming a stationary configuration. So it depends only on this big T and big phi, which is the difference between angles and difference between times. And the result is a sum over Gaussians at different points on this plane. And these Gaussians always have the same fall off or same width as defined by these LT and L phi. And different peaks are suppressed with each other with a factor of e to the minus gamma, the Lyapunov exponent. And the separations between the peaks are determined by the tau and the delta, by integer multiples of tau and delta. Now, this is how it looks like when it's plotted. So this is the T phi plane. Okay, and I'm just plotting the result that I showed you before. We always have a peak at the origin, which means that always the correlation is, or always the fluctuation is correlated with itself when you're very close. But then the special feature that a black hole has, that there appear other peaks that are well separated from the first peak. And the separation is determined by this tau 0 and delta 0 in these two different directions. And these are the these are the critical exponents tau and delta that I was talking about. And there's also an amplitude suppression between two peaks, which is e to the minus gamma. Now, these are the only universal features in this in this correlation function. And the non-universal features is really what the shape of each peak is. But it's a self-similar image. So if I would have here some shape, it will be repeated in all the other peaks, the same shape, but only at different positions and suppressed by this factor v to the gamma, e to the minus gamma. Okay, but and in particular, the width of the peaks is also non-universal. It depends on the statistics of the fluctuations in the emissivity of the disk. That's what we assumed before. These are these LT and L phi. And that's why I was happy that these LT and L phi are actually smaller than the tau and the delta, because if the LT and L phi would be very large, and all these peaks would kind of converge with each other and we would not see any signal. But if actually we see a peak with width much smaller than tau and delta, the separation, then we're in business. Then we can really hope to see a well-separated peak. So this is kind of the main result of this analysis. And of course, as I said, why I think our model is still useful, because all these universal features, the separation with tau, delta, and gamma and all that, that won't depend too much on the shape of the peak. But if we take really a more realistic model of accretion, we may get a more interesting shape here of the peak, for example. So that will also contain interesting information on the statistics of the accretion flow. So that's, but this observable actually allows us to separate very nicely the things that are non-universal from the things that are universal, and both can be read kind of separately. Okay, so we generalized our story to, okay, I'll wrap up in very shortly. We generalize this calculation also to any inclination. It's a bit more involved, but we also have an analytic calculation for general inclination. But it's kind of involved, and it really requires more study. So that's something that we definitely will do. And also, in this paper, in this last paper, we did expand our result to leading order and inclination. And sorry, we showed that this structure that we saw in the polar case actually persists to leading order and inclination. So it's not like a very fine-tuned thing that you have to sit exactly on the pole. Even if you go to 17 degrees, for example, you will still see a similar thing. And so observational prospects, we also had an analysis of observational prospects in our paper, like a preliminary one. This really demands more work to understand better. But just to make like the very simple points. So first of all, seeing more than one peak in this correlation function would be measuring the photon ring, because really for any object which is not a black hole, we can't expect to see any other peak except for from the one in the origin. There's no reason, because these other peaks can only appear when you have geodesics that undergo more than one half orbit. So this would be a strong signature of the photon ring, of the existence. Now, this can also test strong field GR, because all the structure of the many peaks, of course, we won't be able to measure an infinite number, but the more we will be able to measure, the better. And all this structure is really constrained only by the mass and spin of the black hole. And maybe some things depend on inclination, but that's it. So if you measure the locations of these peaks, and maybe even the relative magnitudes, then you can start saying things about the mass and spin of the black hole. And specifically, okay, so the mass, we have already pretty good ways to know what the mass is, to, I don't know, to 20% or so. But okay, so our measurement, proposed measurement can also tell us what the mass is, because the tau really depends on really is related naturally to the mass, because it doesn't depend a lot on spin. For at least for 17 degrees inclination, it doesn't depend much on spin. You see that it varies with spin like 1 m, and the total tau is like between 15 and 16 m. So that's for 17 degrees. So tau is a good measure of the mass, and then delta is actually a good measure of the spin. This delta, which is related to the frame dragging effect. So once you know the mass, if you measure delta, you can tell what the spin is. And that's very interesting because even for M87, we really have no idea what the spin is. And that will be very interesting to try and measure. And just to point out that the main advantage of this method is that you do not need to resolve the width of the ring. You do not need to send the mission far away into space. You can actually work with the equipment that we currently have. The only thing that we do need to do is wait long enough and collect enough statistics. So we just need to sit on the telescopes for a long enough time and collect the visibilities as a function of time for a long time, and then to calculate these correlation functions. And yeah, so that's an advantage. We don't need to like fully resolve the image. So I'm done. I told you about this new observable for the Event Horizon Telescope that we proposed, the 2-point function of intensity fluctuations on the photon ring. This demands a lot more work. So first of all, to understand better what's the signal from any inclination and any spin. Specifically, you can go to the equator at high spin. You can see, I'm sure, things that are significantly different from what I showed you here. So there is a richer structure here that needs to be still explored. You can think of a more observable. So, okay, what happens if I think about more general correlation functions? What happens if I look at correlations of polarization? So there is still a lot of stuff to explore here. And I think the most exciting thing would be to actually measure this. And I hope that our friends at the Event Horizon Telescope will are working on that. So thank you.
I have a question.
Yeah.
How much do you have to increase the current resolution of the EHT in order to be able to make a measurement of the kind that you are proposing?
So I think actually that you don't need to increase the resolution too much. What would be very beneficial, like for example, it is true that if we send a radio telescope out to space and increase the baseline significantly, that will also be great for this measurement as well. But I think that the main advantage of this measurement is that it doesn't require a space mission. It can work already with the current baselines, but it will really benefit from more stations on Earth. And that, for example, the photon ring, the image measurement itself won't benefit a lot from putting more radio telescopes on Earth, but this thing would, because this gives you more statistics. And also it will benefit from just sitting for a longer time. I mean, there's a lot of a lot of people want to use these radio telescopes for various different reasons, but yeah, but I mean, if we can get and we did a preliminary analysis, so if we can like average for like a few months or so, we believe that some initial measurements of C could be possible of this correlation function. It also depends what the target is. So you can think both about M87 and Sagittarius A star, the black hole in the center of our galaxy. They kind of have the same angular width in the sky. So size-wise and resolution-wise, they're kind of the same. But the big advantage of Sag A star is that it's much more variable. So if when you're thinking about kind of averaging over times, this source is much more, varying much faster. So it has much more fluctuations for a given observation time. I mean, there are other problems as well, like there's a time barrier for the EHT for how fast they can form an image. At the moment, it's something like 5 minutes, and Sag A star varies on the scale of seconds. I mean, its M is the scale of seconds. So that's also an obstacle currently, but I don't think it's an acute one. I mean, yeah, it demands also a bit more thought, but it's also possible that we can translate our observable directly into visibilities as a function of time, like into the how to compute that directly from the data without going first to form the image and then compute the correlations in the image, but going directly to the Fourier components. So so yeah, I mean the short answer is that I think that it is possible from Earth. With it only depends exactly how long do you need to average over, but yeah.
Are you looking into any sort of actual, rule of thumb estimates on how much data you need to gather, how strong the variability needs to be,
Yeah,
how many telescopes you need?
right. So we do have that. We do have. I mean, we did that analysis in the paper. It's a very rough and first analysis. So as I said, I would prefer to do this much more carefully. But at the moment, with all these obstructions of how long it takes us to form an image, it seems like that Saj star is actually a better candidate because of this fast variability, and that with the current equipment, which is the order of 10 radio telescopes, um, like 10 stations on the Earth, we would need something like a few months of averaging. So it's still a lot of time on the equipment, but I think it's much cheaper than building a space mission, and will happen much faster. So, and also, I mean, it's not like we need to sit on the source all the time. It's but it would be good to sit like for different periods along these few months, to dedicate it to that.
But what do you mean? You don't have to sit on the source for the same length of period of time of the variability? So if Saturday star is 20 seconds in light crossing time, don't you need to? If you miss 20 seconds, then you basically lost everything.
Right, but I mean, in any way, there's the Earth is rotating, so you don't have to. The telescopes are not like used on that specific goal the whole time. Well, yeah, I mean, right. I mean, and also, I mean, you can just stop averaging for a while and then continue later. It's not like. I mean, if there's something urgent to look at with the telescopes and something else, I mean, it can be done in segments. That's what I mean.
So 1 month a year at each telescope for 10 years should.
I think, yeah, according to our preliminary analysis, yes, for Sagittarius star.
By the way, do you know when the Event Horizon Telescope is planning to release an image of Sagittarius star?
Yeah, I don't, but because they're very good with keeping the information, but I know they're working on it for a long time already, and I know that I just talked to them yesterday, to Michael and George and Alex. I mean, it's I think that they're also something they were trying to do for a while is make a movie of Sagittarius star. I think they thought that after the great success of the image, the next step is the movie. But I think they're having trouble generating this movie, and at least what I heard from them already a while ago, like a year ago, is that the problem is the high variability of the image. So maybe it's kind of hard to see anything coherent there.
Can I ask you, I want to go back. So let's say that you're seeing this correlation function. What physical information you expect to get about the inner structure of the disk, or anything that you cannot see by direct resolving the disk?
Right. So really there are two parts. This universal part determined by gamma, delta, and tau, which is the one that I focus on more. And there's the other part, which is basically the shape of every peak. The shape of the peak itself, which gets repeated in all the other peaks as well. So I think that the shape of this peak will tell you something about basically this 2-point function of the emissivity, delta J. So it tells you something about the statistical properties of the accretion flow. I mean, this is only the emissivity and not like the flow, but it's of course related in non-trivial ways. But it does tell you something about the statistics of the flow.
Such as what? So you expect the flow to be, having I don't know, fluctuations of the certain frequency, or like what kind of what would be your expectation? I mean, what would you expect to see there?
Yeah, I mean, well, first of all, I mean, one thing that I can say that is not really realistic in our model, and that I'm pretty sure would be different in a realistic model, is that these peaks will not be kind of symmetric. There won't be a perfect separability between these t and phi directions, because the flow is actually has a preferred direction, a rotation direction. I think these peaks will look something more like this because of the flow velocity. So there's like more correlation if you look at some fluctuation and then fluctuation going with the direction of the flow, than if you look at some fluctuation then against the direction of the flow. That will have much less correlation. So this can tell you, for example, something about the velocity of the flow. But it's also complicated because this velocity is different in each radius. So, but yeah, like for example, right, but in this case, for example, if you're looking for a polar observer, then you're really probing only one photon shell radius. And then like this angle in which this is elongated can tell you about the velocity of the flow at the specific r tilde 0, which is the photon shell radius that you're viewing from the pole. So this is, for example, something about the velocity of the flow.
Okay. All right, thank you.
Any other questions, maybe from any of the students or postdocs? Questions? Okay. If not, let's thank Shahar again.
Thank you.
Thank you.
Thanks.